Hi and welcome along to a whole new topic. Gravity, all part of electric fields, gravitational fields, eventually magnetic fields, capacitors as an application of electric fields. Lots of stuff to discover here, lots of stuff that works well together. One of the nice things about doing gravity, we get to go and look at circular motion again. So I think that a lot of things fit together here. It's a nice piece of work. A few things to get our head round, but as I say, it builds into a consistent set of rules that we can use in lots and lots of different situations. So, looking at this, you might well think I've lost it, and to be honest, I nearly agree with you. I spent a very long time assembling all these ridiculous bits of clip art. Probably should have drawn it myself, but the honest answer is I was drinking a cup of tea. You can't really talk over a PowerPoint when you're drinking a cup of tea or a bit of paper, so I thought, you know what, John, you find all the bits and pieces, um, assemble them into a picture while you're drinking your tea, and then you can tell the story. So the scene is, well, I'm sure you know what the scene is. It's obviously something to do with Newton and an apple. I find the story of Newton and the apple slightly frustrating in that there are clearly things that don't quite make sense about it, and you hear people say things that can't possibly be true. For example, you might hear people say that Newton invented gravity, as if that before this scene, if you'd fallen over in the street, you wouldn't have hit the ground, you'd have just floated off. Clearly not true. Gravity was known as the force that kept things on Earth. It acted and people obviously experienced it and people had a name for it. What Newton did was make the law universal. He realized that gravity had a wider effect. Newton was part of a community of scientists and physicists, and what many considered the problem of the age was that we had a good understanding in terms of observations of the solar system. So we knew, for example, the Earth and the other planets were going round the sun. And we knew that some planets, like ours and Jupiter, had moons, and these moons were going round the planets. And they knew, perhaps not quite in the level of detail that you knew, that if you want something to move in a circle, then you need to apply a force to it. But of course, what nobody really knew at that time was anything about this force or what was causing this force. So this is the John Clinch version of the story. I think the main benefit of my story, I don't think I score any more on truth, but I think perhaps my story at least reveals actually the conceptual leap forward, what the intellectual contribution of Newton to the world at this point. So we know for sure that Newton was in Lincolnshire. There's a little bit of personal interest for me because he grew up just nearby to where my mother grew up. So he was adopted. Well, his mother moved in or married a local vicar after she was widowed, and he grew up in a vicarage. That's the house supplied to kind of the guy who runs the local church. And my mum grew up in a vicarage within 3 miles of where he was. So he was back home, something we can all relate to now because there was an epidemic. People were very scared of rural areas. Plague was a much more serious illness than COVID-19. So people generally, if they could, fled to rural areas. And while he was there, we understand that he was contemplating, he was thinking about thinking about problems of physics. And what I like is the idea that he's out in the garden. There's an apple tree, and he sees an apple fall from the tree, and it's so often the case during the day he can see the moon in the sky at the same time as the apple. So he kind of he's looking out in this direction, and he's seeing the apple, and he's seeing the moon, and he gets the idea that we know that the force of gravity is pulling down, or the weight is pulling down the apple because the earth is attracting it. But then he sees another spherical object, and because he would have had an understanding of circular motion, he would have realized that the moon is also falling towards planet Earth. The moon is falling towards planet Earth. The apple is falling to planet Earth. They are both pulled by the same force. They are both pulled by the force of gravity. So in this moment, he makes the law of gravitation universal. It applies to all things in all situations. Every object in the universe with a mass pulls on every other object in the universe with a mass. He made some assumptions about how that force would vary with distance. We'll get to those later. And within a day had shown that the model that he'd come up with for gravity was consistent with the very accurate observations of the motion of the planet. So we'll get on to a bit of maths now and change medium for that. So we'll have a look now at the maths of what Newton said. He didn't write it quite in this form, but Newton's universal law of gravity. He said the force of gravity between two objects depended on their masses multiplied together. And he said that the force varied with distance as 1 over the distance squared, and we'll discuss more about the significance of that later, but 1 over distance squared. Okay, so quite important we get this R right. We're going to be dealing with a lot of spherical objects like planets and moons, and it might be that sometimes R is the radius of those objects, but we really mustn't think of that R being a radius. It's the distance between the 2 point masses in meters. If you're dealing with, so when I say point, they're meant to be infinitely small. If we're dealing with spherical masses, it works just as well, but it's the distance between the centres of the two objects, not the radius of the objects. M1 and M2, obviously the mass of the two objects, and they obviously have to be measured in kilograms. And there's the force, and then perhaps not surprisingly, there's a constant that ties this all together, Newton's universal gravitational constant. I'll just get the value from the data sheet. I use it enough that I know it, but it's always worth just checking, where it is on the data sheet. So there we are. Gravitational constant. Units are newtons, meters squared, kilograms to the -2. That's just a constant unit. 6.67 times 10 to the -11. It's actually quite a small number. Gravity is usually regarded as a very weak force. We probably mentioned that in the first year. So G. Now, if you remember Newton's laws, there's not really a lot more to say about this. So if we can imagine the Earth and the Moon, and you'll see on the worksheet in a moment, I think you're going to get to work out the force of gravity between the Earth and the Moon. Again, this distance thing is the only thing that throws people. When you're given the distance from the Earth to the Moon, it's always centre to centre, the one that you need in the equation. The key thing here is that both objects feel exactly the same force, and that's by Newton's third law. Body A exerts a force on body B, that's that force. Body B exerts an equal but opposite force on A. So those two forces are equal and opposite. And that applies just as much to you. Okay, so Earth is pulling you down, that's the familiar force of your weight, but you're also pulling up the planet towards you, and we'll have a lot more of a look at that in the next bunch of work on fields.